Okay, so let's continue our process to get the MGF. In the previous video, we talked about the tool that we can use, which was the differentiation of log, natural log. So we're gonna use the tool in the process which we were dealing with in the previous video, right? So let's keep doing the process. So to review very quickly, as was the scaled x bar, so it was x bar minus mu divided by sigma by the standard deviation of x bar, which is standard error. So it was s, and it was scaled x of x bar, so we were getting the MGF of scaled x bar. We just did that just because if we just treat the distribution of x bar, which is the mean of mu, and the standard error, which is the standard deviation of x bar, as standard deviation divided by square root n, and it's squared, and it'll be variance, right? But when we're going to increase n really like to infinite to see actually the central limit theorem works. But the problem was if n gets really large enough, this part will get large enough because there's n, and because the denominator gets larger and larger, the whole number will get smaller and smaller, a and b, right? And a gets larger, then the whole number gets smaller. So it gets smaller and smaller. So like in theory, like theoretically, standard error goes zero. Like practically it doesn't go zero. It just like converge to like certain level, but theoretically it goes zero because n is gonna be like very large. So it just doesn't express distribution anymore. So it does this distribution something like this because it has standard deviation. But when it goes zero, which means standard deviation is zero, so it just becomes a point, one point, which is mu here. So it's hard for us to see whether it becomes a normal distribution. So my idea was to get a scaled value of x bar, and so that we can actually get rid of the influence of n during the calculation. So yeah, so let's continue our work here. So we put log like on the left side and also on the right side to treat this n like more easily and make the whole calculation easy. So we did this as t, and also here. So we could, by the property of log, we could take this log into here, and log expectation like this, right? And to investigate the how the central limit theorem works, we put n into infinite. So both sides, n goes infinite, and also this side. Yeah, let's write it here. N goes to infinite. And the another thing that we did here was we put this, which is 1 divided by square root n, as y, which means 1 divided by n would be y squared, and n would be 1 divided by y squared, right? So we put y here to permute. So we can change the whole calculation n into expressed as y, not y, but like here it would be y squared divided 1 divided by y squared. So it's going to be something like this. Left side would be the same, and the right side would be when n goes infinite. When n goes infinite, it's going to go infinite, and this value would go 0, right? So we can see that y, let's see here, so n goes infinite, it's going to go 0, so n becomes 0. N would go 0, so I mean y would go 0, so we can write it something like this. And here, let's clear up. N here would be 1 divided by y squared. So 1 divided by y squared, it would be n here. And ln expectation e, and 1 divided by a square root of n is y, right? So t times y, and the remainder goes the same, like this. So we can express it as numerator and denominator. I mean, as a fraction form. So let's do it. So when y goes 0, the numerator would be like this: t times y, x minus mu divided by a standard sigma, and the denominator would be y squared. And we saw that when y goes 0, this part will go 0, right? And because y goes 0, this whole part will go 0, and the exponential of 0 is equals 1, right? So the inside of expectation is 1. So this would be 1, but there's log here, right? Because it's inside of the log. So log 1 would go 0. So we can see that it's 0 divided by 0 form, which is the perfect condition that we can use a hospital rule. So to do that, we had to have a concept of differentiation of log, so which we dealt with in the previous video. So this was the review so far, and let's continue our work on the next video. Thank you.